Thank you for the opportunity to be here. I know it's getting late for many of you, so I'll just say, so my name is David Dunsky, and I'm going to be talking about shocking signals from CHAMP cosmic rays. And this is work done with my advisor, Lawrence Hall, and Keisuke Harigaya. So why CHAMPs? CHAMPs, or charged massive particles, are particularly interesting because they're well motivated both from particle physics and cosmology. So in particle physics, you can have CHAMPs arise from the kinetic mixing between our photon and a dark photon. So you might expect, for instance, a CHAMP with a charge of order 10 to the minus 3 to arise if in case there exists some dark particle that's charged under both our U1 and a dark U1. And then you can write down, for instance, a one loop diagram connecting, say, some dark photon to our photon that you might expect would give rise to a CHAMP with a charge of order 10 to the minus 3, one loop suppressed. But CHAMP charges much less than 10 to the minus 3 are also natural in many other theories beyond the standard model. For instance, you can consider some models with exotic quarks charged under RSU3, but their own mirror electromagnetism, which in some cases you can use this model to solve the strong CP problem without an axion. In this model, you can write down a diagram that connects a dark photon to a loop of mirror quarks, 3 gluons, a loop of our quarks, and then our photon. Now, you can't just write down one gluon because you just can't contract the color indices. 2 vanishes by Furey's theorem, and so you need 3 at minimum. So this has 1, 2, 3, 4 loops. So it's a 4-loop suppressed diagram. And you can actually calculate this exactly from the 4-loop QCD beta function. And you can show that it gives rise to a charge of order 10 to the minus 8. So the point is, in many theories beyond the standard model, you might expect CHAMPs with some electromagnetic charges that can be very, very small. Related to both particle physics and cosmology is that this extra U1 allows the CHAMP, which may be the lightest particle charge under this U1, to be stable and could be an excellent dark matter candidate. So also related to the motivation of CHAMPs in dark matter is that CHAMPs, which have a very small electric charge, can be thermally produced in the early universe via freeze out or freeze in. So it's an excellent way to populate CHAMPs as dark matter. And particularly interesting is, for instance, this freeze in line, where CHAMPs with some charge of order 10 to the minus 11 of the electron charge can be frozen into the right dark matter abundance, roughly independent of mass. So that's a particularly interesting range of particles that are well motivated by cosmology to be dark matter. So in this talk, I'm going to be talking about the effect of the Milky Way on the dynamics of CHAMPs in the disk, particularly the effect of supernova shocks on CHAMPs, which was first brought up by, I should say, Cherenkov and Kolb about a decade ago. So the outline of the talk is going to be roughly as follows. I'm going to talk first about 3 key rates in the disk, which affect the dynamics of CHAMPs, their acceleration and ejection from the galaxy by supernova shocks, their diffusion into and out of the disk in the local CHAMP flux on Earth, which will allow us to look at the direct detection of these accelerated CHAMPs in various cool experiments. And then if I have time or there's interest at the end, I can actually talk a little bit about how some CHAMPs, if they have a small enough mass or large enough charge, relatively, I should say, can actually collapse into the disk, just like the baryons do when they go from the halo into the disk. So you could get almost a pseudo dark disk for some regions of parameter space. And then I can also talk about a little bit how Fermi acceleration, which is the method at which these supernova shocks accelerate charged particles like cosmic rays, actually work. You know, we're all particle physicists, so we should know how nature's own accelerators work. It's very cute derivation. There's many ways to do it, but it's really beautiful. It just depends on macro physics you can show. And if there's an interest, I can talk a little bit about that and time. Okay, so let me first talk about 3 key rates in a disk, which are effectively given rise to 3 important media that permeate the galaxy. The first is the interstellar medium. The second are supernova shocks. And the third are magnetic fields in the disk and slightly above and below the disk as well. So the first is the thermalization rate in the interstellar medium, which acts to decelerate CHAMPs to thermal speeds. The second rate is a supernova shock encounter rate, which acts to accelerate CHAMPs to shock speeds and actually beyond. And the third rate is the escape rate from the disk, in which these magnetic fields act to confine and prevent champs from escaping. So let's talk about each rate one by one. So the first rate is the thermalization rate in the interstellar medium. Now, the interstellar medium is the plasma with various phases in rough pressure balance, meaning that the number density times the temperature is roughly constant among the different phases, but they differ in their various number densities, their temperatures, ionization fractions, and filling volumes. Now, the reason why the interstellar medium acts to slow these champs down is because there is little soft scattering between the champ electromagnetically and the protons and electrons in this plasma. And so there's a little there's a little change in momentum with each soft scatter. So after the buildup of many of these little soft scatters, the total little delta P equals the original champ momentum, you can slow the champ down to thermal speeds, and you can define a rate effectively at which this occurs, which is just coming from the scattering cross-section from just Rutherford scattering. Now, it turns out that the warm ionized medium actually dominates the thermalization rate for champs, just because it has the largest number density of electrons and fractional volume, filling volume. So for a typical champ mass to charge ratio squared, m over q squared of roughly 10 to the 6 GeV, where q is in units of the electron charge, and a speed of roughly 10 to the 3 kilometers a second, you may expect a thermalization rate of 1 every 40 million years. So that's the rough time scale for a champ of this mass to charge ratio and speed to slow down. Now, the important thing is in this equation is this velocity to the -3 power, and that's just coming from this Rutherford cross section, the 1 over v cubed in that cross section. And the important thing is that the faster a champ is moving, the much harder it is to slow down. And so this is going to be very important when we talk about supernova shocks and the ability of a champ to be Fermi accelerated, which relies partially on the champ being faster than the shock itself. So champs which encounter one shock can remain superthermal for very long periods of time, way longer than typical protons and electrons. And they can encounter a second shock and be Fermi accelerated because they're moving faster than the shock itself. I'll talk about that a little bit more detail in a bit. All right, the second important rate is this shock encounter rate, which is intimately tied to the rate at which champs can be Fermi accelerated, because the shocks are what's doing the actual acceleration of the champs. Now, the shock encounter rate depends on the velocity of the shock, because it depends on the typical size of the shock, which is velocity dependent. So for instance, the rate for a champ to encounter a shock of speed vs is roughly the volume of a supernova with that shock speed over the volume of the disk where the supernova are located, times the rate at which supernova go off in the Milky Way. Now, the supernova shock starts off life roughly around 10 to the 4 kilometers a second or so in this blast wave phase. When the mass encountered of this shock roughly equals the mass of the ejecta, mass that it's carrying with, then what happens is it enters what's called the Sadov-Taylor phase, where it slows down now with a radius versus velocity relationship that goes as r goes as v shock to the -2/3 power, which will be important later. And this is just coming from energy conservation. So the shock speed is dropping. And what happens is once it goes below around 100 kilometers a second, you can have neutrals begin forming at the shock front. This is because they're not moving fast enough to collisionally ionize the particles at the shock front itself. And this is a very important transition, because actually once neutrals begin forming at the shock, they start disrupting the magnetic field, the moving magnetic field at the shock front, which is actually responsible for the Fermi acceleration itself. It's causing the reflection, which is going to give rise to the momenta exchange to the champ. So basically after the snowplow phase, where the neutrals begin forming at the shock front, you can't have Fermi acceleration, or it's very inefficient. And the shock will just drop in speed until it merges with the interstellar medium at roughly 10 kilometers a second or so. So if we look again at this encounter rate, it grows with the largest volume of the supernova shock that can effectively Fermi accelerate a champ, which is going to occur right before, or right at the end, I should say, of the Sadov-Taylor phase, near the beginning of the snowflow phase, which for typical interstellar medium values would give rise to a supernova radius roughly around 40 parsecs or so. So you can just enter these various numbers, the 40 parsec supernova shock with a disk radius and volume, typically of 15 kiloparsec radius, 300 parsec height, and about 2 to 3 supernova per year. You might expect a shock encounter rate of roughly once every 25 million years, independent of champ parameters, of course. All right, I'll talk a little bit briefly about Fermi acceleration, not the derivation per se, before going on to the third rate. And the idea about Fermi acceleration is it basically is the same mechanism of acceleration or imparting momentum, just as like a ball gains momentum when it reflects off like a moving wall, for instance. In this case, you get some change in momentum that's proportional to the momentum itself. So if the champ is actually moving slower than the shock, it's basically accelerated just to the shock speed itself. But if it's moving faster than the shock, then what happens is it's possible reflect back and forth across the shock front and repeatedly reflect off this moving wall. It's the moving magnetic fields which are causing this momenta exchange. And in that case, it can give rise to a exponential momentum gain, because each momentum gain is proportional to the momenta itself. And this is what's called first order Fermi acceleration, and it gives rise to these beautiful power law spectra, momentum power law spectra that we see, for instance, in cosmic rays today, as shown, for instance, on the right here. So now you'll have to trust me, because I'm not going to do the derivation now. Maybe if we have time, I said we could talk about it a little bit later. But the ability to be Fermi accelerated just depends on two ingredients. One is that the champ is initially moving faster than the shock, so it can actually reflect back and forth across the shock front itself. And now, what's actually pretty interesting is that this is easier for champs than normal protons and electrons, because champs actually have a very difficult time of slowing down, as we saw from that thermalization rate, since generally their mass is either quite large or their charge is quite small. So they can remain very, very fast between encountering a typical shock. So if they're moving initially slower than a shock, they can say be accelerated to the shock and then wait 25 million years or so and encounter another shock. They're still moving very fast and they could be Fermi accelerated at that other shock. Or if they're moving already at the virial speed and they just never slow down before encountering another shock from thermalization, they can be Fermi accelerated in one go. And so actually, champs don't really have what's called this injection problem, which normal protons and electrons do, because normal protons and electrons are typically at thermal speeds, and it's very difficult for them to satisfy the condition of being faster than the shock front itself. But obviously, some very small fraction of protons and electrons can satisfy this, and those are injected, we believe, to what forms these cosmic rays that permeate the galaxy and create a flux of cosmic rays on Earth. So the second condition is that the champ must reflect backwards. This just imparts the momenta. If it doesn't reflect backwards, it's not going to get any momenta exchange. And so this is actually not accomplished by particle-particle scattering. It's accomplished by scattering off the magnetic fields that are moving around the shock. And so this, since it just is related to the magnetic field, it's the ability to reflect goes as a gyro radius, which is linear in Q, not quadratic, which means that you can actually, champs with very small charges can be influenced by supernova shocks. It's actually quite powerful. So the third rate is the escape rate from the disk. And let me walk you through a little bit about what's going on here. It's a diffusive process, and that champs diffuse through the interstellar medium by resonantly scattering off magnetic irregularities, these delta Bs, which are typically on the size of their gyro radius. So they resonantly scatter on these irregularities on the size of their gyro radius. So for instance, let me just show you diagrammatically the picture of what's going on here is that you have some uniform magnetic field, roughly uniform magnetic field B, typically of order of micro-Gauss in the disk. And you have some inhomogeneity, this delta B, which is a function of scales. It's related to the power spectra of the magnetic field in the disk, but it's some little fluctuation, which makes some little angle delta theta with the uniform field. And this delta theta gives rise to a change in pitch angle, the same delta theta. What a pitch angle is just the angle between the velocity of the champ and the total magnetic field. So this causes a slight little pitch angle change, very small, of order delta B over B. Now with each scatter, the champ is going to effectively scatter uncorrelated off one of these little fluctuations. And this gives rise to a random walk in angular space. So you can look at the RMS delta theta squared, or the RMS delta theta roughly, which is the number of scatterings approximately times this little delta theta squared, just a random walk in angular space. Now you can define a effective mean free path when this delta theta is roughly, of order pi, or so order 1. It's completely lost track of its original position. This gives rise to an effective mean free path, effectively the distance traveled roughly, or the distance diffused, which is n, the number of scatterings, times the gyro radius, because these irregularities are scattering of order their gyro radius, which you can see this is order 1. This just tells you this is the mean free path is the gyro radius over this delta theta squared, which is effectively this delta B over B squared. Now, since this effectively power spectra, these fluctuations are scale dependent, this is necessarily goes as some gyro radius to some power A. So it's not necessarily linear in the gyro radius. In fact, we can determine this empirically from looking at the cosmic ray secondary to primary spallation ratios. And this is just because we've measured very well in the lab the colliders, the spallation cross sections for various nuclei. And then what we can do is we can look at the ratios that we receive of cosmic rays of the parent to children nuclei. And we can see how that changes with effectively the gyro radius and the momenta of the champs, or excuse me, of these cosmic rays. And you can do that from that infer the gyro radius scaling of this mean free path, because you can determine the effective distance that each traversed, and that tells you the relative abundance of the primary and secondary cosmic rays. And so what's actually observed is that this A power, the mean free path, is proportional to the champ gyro radius to roughly the 1/2 power, is what's observed. And with this mean free path known, you can determine a diffusion constant, which is roughly the mean free path times the champ speed. And from this diffusion constant, you can determine an escape rate, which is roughly the inverse time scale for a champ to diffuse a given distance. Take it to be, say, the disk height away from where the typical supernova lie. And for instance, for this m over q, again, this fiducial 10 to the 6 GeV, you find an escape rate. It's again roughly 1 every 20 million years. And it goes as the v to 3/2 power times m over q to the 1/2, which will be important for us a little bit later when we look at the spectra of champs that have escape actually, or that are on Earth, and those that have momenta that would be able to escape. So the key thing is that the escape rate increases to the 1/2 power roughly with the gyro radius. All right. So with these 3 rates in hand, let's see exactly how they interact and they're related to determine the shape of the accelerated champ spectra that we would see on Earth. Okay, so I've drawn the 3 rates as a function of champ speed for, say, a fixed mass and charge. So in blue, you have the thermalization rate, which drops to the -3 power in velocity roughly. So it drops quite a bit as the champ speed grows. You have the escape rate, which grows with velocity just because it grows with the gyro radius. And then you have the shock speed in this magenta, which is independent of champ parameters, roughly once every 20 million, 10 million years or so. So we define before going on right here, we just define real quickly this V1, V bar, and V2, which are the champ speeds at which the various rates are equal. So for the champs actually in the Milky Way, it turns out it's somewhat galactic dependent. Whether V1 is greater than V2, it depends a bit on the galaxy. But for the Milky Way, for all charges less than roughly 10 or so, this V1 is less than V2. And namely that the rate at which the speed at which the thermalization and shock rate are equal is generally always slower than the rate at which the shock rate and escape rate are equal. So this V1 and V2, which will be important for demarcating where you'll get changes in the slope with the spectra coming up. So just keep that in mind. So let's see exactly how this champ spectra can be determined roughly from these rates. So when you have a supernova shock go off, you're going to create a dn, dl, and v spectra, which is proportional to the probability of encountering a shock, which goes as a volume. And we know how the radius versus volume relationship is determined. It's dominantly by the Sadov-Taylor phase. That's where most of these dynamics are occurring. So the radius goes as v to the minus 2/3. So that means that this creates a dn, dl, and v spectra, initially of v to the minus 2. So what this means is that it's just telling you that it's much more likely to encounter a slower shock than a faster shock. What we're going to be doing is we're going to be looking at dn dp, which is a little bit more fundamental, in that actually it transitions nicely, basically continuously from non-relativistic to relativistic regimes, where the momenta is just defined relativistically or not. So if dn, dl, and v goes as v to the minus 2, that means dn dp initially goes as p to the minus 3 power. Okay, so initially you have some spectra that goes as p to the minus 3 all the way to p blast, where p blast is the momenta of the champ, such that its speed is roughly 10 to the 4 kilometers a second, which is the typical initial shock size, shock speed of a supernova. So what happens next is that thermalization eats away at the slower moving champs. Remember, the slower champs are thermalized first. And you can show from this evolution that the momenta drops as p squared. So with time, the momenta drops as so, such that after time 1 over the shock rate later, roughly, the spectra is shown by this orange, roughly, and this blue, and it's peaked at P1. This spectra, or these champs, are moving faster than the shock itself, and they can be Fermi accelerated to this nice cosmic ray p to the minus 2 Fermi accelerated spectra, which is shown by this green here. Now what happens is that the champs with momenta greater than P2 are actually more likely to escape before you encounter them before another shock and detect them on Earth, with a probability roughly the ratio of the escape rate to the shock encounter rate, which goes as a gyro radius to the 1/2. And so these champs are actually suppressed because they're more likely to be escaped. These are the champs you see on Earth. So it's reduced by a factor of roughly p to the minus 2 to roughly p to the minus 2.5, which is actually what you see with cosmic rays on Earth. We can't see below here for cosmic rays because they actually can't reach the Earth roughly. They're too slow speed to bypass the solar wind. So we see the p to the minus 2.5 spectra on Earth, but in general for cosmic rays, but for champs, it's p to the minus 2 up to this p2, and then p to the minus 2.5 above. So the key thing is that you see that champs to be Fermi accelerated must actually encounter a shock of speed v1 to be Fermi accelerated. And for slower moving champs, this means that they either have to encounter 2 shocks, one to accelerate them to super thermal speeds and allow them to remain non-thermal up to 25 million years later, or champs with m over q squared greater than 10 to the 5 GeV are actually have a large enough mass to charge ratio that they can remain at the virial speed and not thermalize in 25 million years. So they can be Fermi accelerated in one go, basically, one shot Fermi accelerated, and they can be efficiently ejected from the disk. However, that's not the whole problem, or that's not the whole solution, because we don't know this normalization of the spectra. And just because the champs can escape doesn't mean that they can't diffuse back in. In fact, if they can escape, there are champs in the halo that can replenish them. So what we have to do is solve a rough transport equation in the same line of how cosmic ray propagation models are discussed. So for instance, what we look at is a model of the Milky Way where we have effectively a diffusion region, which we actually know goes from the disk all the way up to roughly 3 kiloparsecs above and below the disk, where this diffusion can occur. So this is observed. We observe this hot gas that we know is causing this scattering and diffusion to take place. So we can write down a system of coupled PDs where we have the rate of change of the number density of champs, of the unaccelerated champs. They diffuse in this region, but they actually, you lose them from acceleration if they're in the disk, with roughly this acceleration rate of encountering a critical shock. whereas the accelerated number density increases for those number density of champs in the disk at rate of the critical shock encounter rate, minus those that escape. So we can determine this evolution with boundary conditions such that the number density just matches to the typical dark matter halo number density, roughly 0.3 GeV per centimeter cubed over M on these boundaries. With this numerical calculation in hand, we have the number density spectra of champs, and we can use this for direct detection to determine various signals. And it leads to some very cool signals in the mass to charge parameter space. Since champs can easily reach underground detectors. They're moving much faster now in some regions of parameter space. There's no overburden problem for many of them. 2, champs below a GeV can actually impart nuclear recoils above the keV threshold of many experiments. 3, champs are strongly ionizing and can produce these DE/DX ionization losses in many detectors. And 4, this is a very cool one, is that relativistic champs can emit or induce Cherenkov light when traveling through water detectors like Super K. I'll talk very briefly about just these barriers to detection before going to the direct detection. I guess I have about just a few minutes. How much time do I have, by the way?
Well, a few more minutes, let's say 5, maximal 10, I would say.
Okay, perfect. So let me just briefly discuss this. That there are 2 barriers to detection. There's a solar wind, which is this plasma emanating from the sun, which prevents charged particles from reaching the Earth. It's kind of like they have to swim upstream to reach the Earth. So you have a flux that carries them away. You have a flux that's, you have a flux that carries them away with a solar wind speed and a diffusion inwards. So at equilibrium, you would expect actually a number density, the flux to be 0, and a number density that's roughly exponentially suppressed as you go closer to the Earth. And in fact, this is what the Voyager 1 and 2 spacecraft observed, and which have left the solar system. They were counting these various cosmic rays as they traversed radially away. And from that, we can determine the mean free path of champs in the solar system, this diffusion constant roughly, and look at the suppression of champs shown in this bottom left plot, which shows the champ gamma beta versus M over Q and the suppression to reach the Earth. So champs that are moving slower than the typical solar wind speed, roughly a couple hundred kilometers a second, and very low masses, which can very easily scatter, are very highly suppressed. But actually the dominant barrier is coming from the overburden of the crust. For instance, champs trying to pass through Gran Sasso to reach like detectors like macro have DE/DX losses, which require even larger gamma betas to reach. So I'll just skip that and just discuss the results, which are just the results from the various experiments. So nuclear recoils, we have just champs scattering off nuclei. We can use our calculated spectra, the Rutherford cross-section, to determine roughly a signal rate per nucleon. So it's just roughly the integral of this cross-section times velocity times the number density of accelerated champs. And what we can do is we can plot, for instance, or we can see when the signal rate is above 10 to 15 signals per exposure time. And these contours show the fraction of dark matter that can be champs in the mass and charge plane. So you can see that these nuclear recoil detectors, for instance, can reach very low charges and very large masses and constrain champs quite powerfully, but they can't actually reach large Q because generally they're veto experiments. They get vetoed by too much electron recoil deposits. Then I'll quickly just discuss Cherenkov light experiments. For instance, champs can cause Cherenkov light over the background in detectors like IceCube, or recoil with nuclei, with electrons and Kamiokande. And these champs are much larger charges to actually create the visible Cherenkov light. And you can put very strong bounds on the fraction of champ dark matter. See roughly 10 to the minus 10, 10 to the minus 14 for very large Q from say Super K, and large also for IceCube. And then last is ionization particle searches. And that champs with very large Q of order 1 can produce DE/DX losses, ionization losses, and scintillation light. And these detectors, such as like macro, which here I show a dedicated search for charged particles versus in Baxan, these are just enormous detectors, which we're looking for scintillation light, for instance, from particles like champs or even monopoles, produce enormous flux bounds. And we show here for the various Q, very close to 1, what the fraction of dark matter is allowed. You see that it's insanely small for Q of order 1 because these detectors are just so large and large exposure times. And we did not see signals. So very, very strong constraints. And then, so I'll just say in sum, just to conclude, here I show just a plot on the right showing the total number of the total constraints that we find for fraction of dark matter of champs being 1. And that for M over Q less than roughly 10 to the 10 GeV, there's a large flux of accelerated champs in the disk today. Nuclear electron recoil experiments, Cherenkov light experiments, and ionization detectors can produce stringent bounds on the fraction of champ dark matter. So thank you very much.
Okay, thanks a lot, David, for this nice talk. So anyone has questions, please? So no one any question?
I have just a curiosity. How can you compute the diffusion coefficient in the magnetic field of this particle with small charge?
Oh,
I assume that is linear, but to me it seems
yeah, because it turns out that, so it just depends on the gyro
it's a
radius.
nonlinear problem, no, in general.
We
It's
say
it's highly
like,
nonlinear, the diffusion of charged particle in the magnetic field.
right. Well, it seems to be well described by just a diffusive random walk. So if you can estimate the diffusion constant, you roughly just know, take into account these.
Yeah, but how you estimate your coefficient A, the one in front of the Larmor radius?
Oh, how is that the 1/2 power determined?
Yes, yes.
Oh yeah. So
Index.
it's determined from looking at the effectively the abundance of parent to children nuclei. And so we can determine how much from that ratio that we see on Earth of various cosmic rays, and we know this cross section, we can determine how much matter they've roughly, how far they've diffused roughly before reaching us.
But not only, no? So the cosmic rays also lose energy and
oh yeah, but if it's above, like these are, so for below like a GeV, you have to take into account other energy losses, especially for electrons, right? You can burn them off much more easily. But for basically above a GeV, the energy loss is very small. The space is so dilute, there's barely any energy losses. So once you're relativistic, the thermalization rate just drops dramatically. So these things aren't really losing energy once you look at cosmic rays, typically above a few GeV in energy. So that's where you're looking about. So you can look at various parent to child nuclei, cosmic rays, determine effectively the distance they travel. And so for different nuclei, they have different charge to mass ratios, of course. And from that, you can infer from various fits, and it fits like very well. I mean, these spectra you saw are very nice power laws. Effectively, how the diffusion constant or the mean free path changes as a function of gyro radius. And for all of these different fits, like many different ways to do it, you get like this 1/2 power roughly very, very nicely. So, I mean, like the power law we see of cosmic rays is very close to a 2.5, 2.6 or so power law. Whereas the supernova Fermi accelerator rate from just pure supernovas is roughly p to the -2, which can be observed in situ as well. So the diffusion constant, those have escaped, you can infer the power law very well. It's just the difference between 2.6, 2.5, and 2. And it holds for all these different charged particles in their various massive charge ratios, and it fits well in with the theory of this resonant diffusion. So I think that, that's how you would estimate it in these various effects.
But also the diffusion volume is completely different, no? So the champs with respect to ordinary cosmic rays.
Oh, yeah. But you can infer actually
So dark
that
matter is in all the halo, no? And the
say that
cosmic
last part
rays,
again.
the dark matter is in the halo, so the diffusion volume is very large.
Oh, yeah, yeah.
The cosmic rays are just in the disk.
Yeah, so the diffusion region actually can be inferred two different ways that they agree roughly with each other. And you can find as well, many of these nuclei are also radioactive, so you can determine a lifetime loss as well and look at a time of where they were or where they, how long they've been effectively scattering and the amount of matter that they've traversed. And what happens is that the amount of matter that they traversed and the lifetime of them, it doesn't agree if they were completely in the disk the entire time, because they would traverse too much matter. So what actually happens is that this was called the confinement region, slightly above the disk, roughly a few kiloparsecs above and below the disk. It's dilute still, but we know that there's actually cosmic rays that they go back up and they come back down. So there's scattering that still is within the disk and a few kiloparsecs above and below. And we know that there's hot gas there, and we can see these cosmic rays scattering there. So the diffusion region is quite large, right? It's not necessarily in the halo. It drops quite a bit, the magnetic field.
But
So
all
that's
these
why, for
details
instance,
are relevant for the bound that you quote.
let's say that
All
again.
these details about the diffusion volume.
Yeah, exactly. Like we take this confinement region to only be where we know the magnetic field in diffusion actually lies, which is roughly like a 3 kiloparsec. We believe like a 3 kiloparsec or so cylinder, to a first approximation within the disk, above and below the disk. So above that, we take no diffusion, so they can just freely propagate roughly.
And how the bound depend on this?
The bounds depend on this?
Yes.
Yeah, exactly.
The bound
So that's
that you quote, I don't know, if you take 5 kiloparsec instead of 3.
Oh, versus 3? Oh, it's a very small change. Yeah. So yeah, so there's a lot of uncertainty in this astrophysics, right? You can't measure this stuff to very high decimal places like particle physics. So there's definitely uncertainty in some of these results. But the thing is that these bounds can be so strong, like on the fraction of dark matter, like 10 to the minus like 14 you saw in some regions. So like, I mean, I would trust this within a couple orders of magnitude. I don't think it's not perfect, right? Because there's just astrophysical uncertainty that's hard to evade. But changing it from 3 to 5 kiloparsecs, or a shock encounter rate from 25 million years to 10 million years to 50 million years, it's not going to change the results that much. But within a couple orders of magnitude, I would trust some of this. So
thanks.
Yeah, for sure.
Okay, any other questions or comments?
Yeah, I have a comment now. One thing I find interesting in your paper is that so you stop now at 10 to 11 GeV.
Right.
But now, if you go above, now implication of your paper is that dark matter with electric charge 1 is excluded even above the Planck scale.
Right.
Which I didn't knew before reading your paper.
Yeah, and thank you for pointing that out. We were so focused on this region roughly below a 10 to the 11 GeV, because that's roughly where this supernova is actually stopped being effective. What happens is actually to the right of this line, the supernova shocks can't impart enough momenta beyond the variable speed. So we were just focused kind of in this region. But I thank you for pointing that out, Alessandro, that, for very large masses, some of these bounds actually extend further, which is part of what Nirmal was talking about. For instance, for like xenon 1 ton, could extend up to like 10 to the 18 GeV if you were very careful with, like, for instance, veto counts for CHAMPs. But some of these scintillation detectors, for which we're looking for monopole searches, are incredibly strong flux bounds. And you can, as you say, Alessandro, constrain CHAMPs above the Planck mass with Q of order 1, which is pretty incredible, pretty crazy stuff. So.
Yes, further comments, questions? So I don't see any. So
sorry, I have another curiosity. If you take a charge larger than 1, 2, and a very heavy candidate, heavy means 10 to the 18 GeV, The bound are still so strong. So you understand what I mean, no? Because the energy losses depend on the velocity. So these candidates are small, and the charge is large. So how these boundary scale? Because it's not intuitive to me, at least.
Yeah. Right. So actually,
because if you increase the charge, the particle cannot penetrate from the other side of the Earth.
right. Yeah. So
It can
in
be
all these
stopped.
bounds. Oh, sorry. Go ahead. Yeah. So in all these bounds, we have to take into account the suppression from the overburden. So for a given m over q. For charge sufficiently large, if they're in the very small mass region and they're not relativistic, they're not going to be able to reach these detectors. And you just have no bounds. That's why.
No, very heavy, 10 to the 18 GeV.
Oh yeah. So for those, so most of those can actually reach the Earth very easily. Even like, are you talking about say Q still of order 1, but maybe like a couple, or is that what you're thinking about, or a little bit more than
larger
1?
than 1. 2, 3.
Yeah. So if it's still of order 1, larger than 1 still, these things are gonna have an easy time to reach the Earth. In fact, for like 10 to the 18 GeV, Q of order 1, I'm pretty sure I was estimating it actually go from the other side of the Earth too. Roughly and traverse.
Yeah, but if you increase the charge at some point,
at some point it's going to stop. At some point, in fact, actually, some of these results will have to be even a little bit more refined, because for Q very large, like roughly, I think we estimated more than 10 or so. The V1 and V2, these escape rates, the speed at which the escape rate, the speed at which the thermalization and shock rate are equal, and V2, the speed at which the escape rate and shock rate are equal, can actually switch places if Q is large enough. So you have to be a little bit careful with that region.
Did you check these or not?
Oh, we did not consider Q less than 1. These results should hold roughly still the same. Like you can just continue them probably with eyeball. It's probably a pretty good approximation up to like Q of order 10 or so. I think that's probably still a good approximation. In fact, even larger, it's probably still, I don't think it would change that much. But the thing is like the Q of order 1 region, like those bounds are insanely strong. So yeah, they may change. They're going to drop a little bit because, as you say, there's more crust overburden, and some of these other galactic dynamics can change a bit. But still between Q of order 10 and below, I mean, I think the bounds are still extremely strong. But yeah, they would change. We didn't consider Q greater than 1, to be precise.
Okay, thanks.
Yeah.